Work, energy, power. I mean, these are words we throw around all the time, right? But what do they really mean in the world of physics? Well, they're basically the secret code for understanding how everything moves, from a simple falling apple all the way up to a speeding supercar. And in this explainer, we're going to crack that code.
So let me start by asking you something. Picture this. You spend your entire day pushing against a solid brick wall. You're giving it everything you've got. You're sweating, your muscles are screaming. It feels like the hardest work of your life, right? Well, according to a physicist, you've actually done zero work. Yep, none. How on earth is that possible? It all comes down to the very specific relationship between work and energy. Okay, so here's the key. The best way to think about it is like this. Energy is like money in the bank. It's the potential, the stored ability to get something done. And work is the actual process of spending that money, of transferring that energy to make something happen, like moving a box across the floor. One is the capacity, the other is the action. You literally can't do any work without using some energy. All right, so here's what we've got on tap. We're going to kick things off with the nitty-gritty of work in physics. Then we'll get into the two main types of energy, potential and kinetic. After that, we'll talk about a law of energy that you just can't break. And we'll wrap it all up with power, speed, and the all-important efficiency equation. Let's dive in. Okay, first up, the physics of work. And here's the absolute golden rule, the one thing you have to remember. For work to be done, something has to move, period. No movement means no work. And that, right there, is why pushing on that brick wall gets you a big fat 0 in the physics workbook. The wall didn't budge an inch. So how do we actually put a number on it? Well, the basic formula is super straightforward. Work is just the force you apply multiplied by the distance the object moves. That's it. We measure it in a unit called joules. But what happens when life gets a little more complicated? What if the force you're using isn't pointing in the exact same direction the thing is moving? Let's look at this Arctic explorer pulling a sledge. It's a perfect example. See, they're pulling on that rope, but the rope is at an angle to the ice, right? It's not perfectly horizontal. So even though they're pulling with a ton of effort, not all of that force is actually helping to move the sledge forward. And here's how physicists handle that. They cleverly split that one angled force into two separate parts, or what they call components. You've got the part that pulls straight forward, the horizontal part, and the part that pulls slightly upward, the vertical part. Now think about it. Is the sledge flying up into the air? Nope. So that upward pull isn't doing any work. The only part of the force we actually care about is the one that's in the exact same direction as the motion. So, how do we mathematically isolate just that useful forward-pulling part of the force? Well, this is where a little bit of high school trigonometry becomes our best friend. The solution is actually really elegant. We just multiply the whole thing by the cosine of the angle. So the full works every time formula is work equals force times distance times the cosine of that angle, theta. Problem solved. All right, so we've established that work is the transfer of energy. What exactly is this energy that's being transferred? Well, in mechanics, it basically boils down to two main flavors, potential and kinetic. You can think of them as the two faces of energy. Let's break it down. Potential energy is all about position. It's stored up energy. That book sitting way up high on a shelf, it's just loaded with potential energy, waiting to be released. Kinetic energy, on the other hand, is the energy of motion. It's the energy that a bowling ball has because it's currently rolling down the lane. So one is stored and waiting, and the other is happening right now. Let's zoom in on potential energy for a sec. A really common type is gravitational potential energy, and it's basically equal to the amount of work you have to do to lift something up against gravity. The formula is pretty simple. It's the object's mass times g, which is just the constant for gravity's pull, times how high you lift it. So the higher it goes, the more potential energy it's got stored up. And now for kinetic energy. This is the energy an object has when it's moving. The formula here is 1/2 times the mass times the velocity squared. And let me tell you, that squared part is a huge deal. It means if you double an object's speed, you don't just get twice the energy, you get 4 times the energy. That's why speed is such a massive game changer when it comes to energy. So you've got these two types of energy, potential and kinetic. And in the real world, they're always flipping back and forth between each other. But underneath it all, there's this one single, unbreakable law that governs everything. It's called the principle of conservation of energy, and it's one of the most important rules in the entire universe. It says that energy can't be created out of thin air, and it can't be destroyed or just disappear. It can only change from one form to another. The total amount you start with is always the total amount you end with. It's the ultimate you can't win, you can't lose, you can only break even rule of physics. And this is just a beautiful way to see it in action. Look at these two graphs. As an object falls, its potential energy, the energy it has because of its height, steadily drops. But at the exact same instant, its kinetic energy, the energy of its motion, rises by the exact same amount. It's a perfect trade-off. One goes down, the other goes up. And if you were to add them together at any point, the total amount of energy would stay exactly the same. And you know what? Knowing this law is like having a physics superpower. I mean, look at this pulley system. It seems pretty complicated, right? You could try to solve it with forces and accelerations and all that. Or you could use conservation of energy. It's like a cheat code. All you have to do is say the potential energy that the heavier block loses as it falls has to go somewhere. So where does it go? Well, some of it lifts the lighter block up, giving it potential energy, and the rest of it turns into kinetic energy for both blocks as they start moving. You just set energy lost equal to energy gained, and bam, you could solve for how fast they're moving. Okay, so we know all about doing work, but there's another piece to the puzzle. How fast are you doing it? And that's where the concept of power comes into play. Power is all about the speed of work. It's the rate at which you're using or transferring energy. We measure it in watts, and 1 watt is simply 1 joule of work done every single second. So think about it. Lifting a heavy box up a flight of stairs takes the same amount of work whether you run or walk. But running takes way more power because you're doing that same work in a much shorter amount of time. And here's a really neat little shortcut for when something's moving at a constant speed. The power it's using is just the force being applied to it multiplied by its velocity. It's a super useful formula that directly connects, say, the force pushing a car forward to the speed it's able to maintain. And this chart really brings it to life. Look at this. For a car cruising on a flat road at about 67 miles per hour, the engine needs to churn out 60 kilowatts of power just to fight air resistance and friction. But now, try to maintain that exact same speed while going up a hill. Whoa. Suddenly, the power needed jumps all the way to 95 kilowatts. It's a huge increase, and it's because the engine is now battling friction, and it's constantly doing work to lift the car's massive weight against gravity. Which brings us to our final big idea. See, in a perfect physics problem world, everything works flawlessly. But in the real world, not so much. Every single time we try to change energy from one form to another, some of it gets wasted, usually as heat. And that brings us to efficiency. Efficiency is basically a report card for a machine. It's a simple ratio. How much useful energy did you get out divided by the total amount of energy you had to put in to begin with? You know, a perfect 100% efficient machine would be a game changer. But sorry to burst your bubble, they just don't exist in the real world. There's always some energy lost along the way. And if you want a jaw-dropping example of inefficiency, look no further than an old-fashioned incandescent light bulb. This is wild. For every 100 watts of electrical power you feed that thing, you only get 5 watts of actual useful light out of it. The other 95%, it's just wasted as heat. I mean, it's basically a space heater that just happens to glow a little bit. And that, right there, is exactly why we've all switched to super efficient LEDs. So, when you pull it all together, work, energy, power, efficiency, it all comes back to that one unbreakable rule. Energy is conserved. It just changes its costume, but it never ever disappears. And that leaves us with one final big thought. If this fundamental law governs everything from a simple pulley to a car engine, where else does it hold true? The answer is everywhere. From the nuclear fusion in the heart of a star to the expansion of the entire universe itself. The real question is, what does this fundamental truth tell us about the very nature of our reality?